Hi there, welcome to my YouTube channel. In this video, I'm excited to share with you a powerful tool that I developed during my PhD thesis, namely a Jupyter notebook for calculating the initial stiffness of the components in the beam-to-column joint element called Inno3DPnPJoint implemented in OpenSys. This element is specifically designed to model the Inno3DJoint system, which consists of tubular columns with cold-formed steel truss girders connected to them. Take a look at this figure illustrating a connection with 4 beams. While this beam-to-column connection may seem complex at first glance, it can be effectively represented by a simple mechanical model with 5 nodes, where nodes 1, 2, 3, and 4 represent the connection nodes for the CFS truss girder, and node 5 represents the connection node for the column. The mechanical model incorporates 3 types of components. In green, representing the connection components, in red, representing the tube components responsible for face deformation, and in blue, representing the tube components responsible for the 3D interaction between the faces of the tubular column. This mechanical model has been expanded to a beam-to-column joint finite element, which can be found in the OpenSys library under the Inno3DPnPJoint class. In this video, our main focus will be on calculating the initial stiffness of the two components using a Jupyter notebook. To access it, simply navigate to my GitHub page. Under the users, repositories, and now navigate to the Inno3DPnPJoint component calculator repository. Make sure you are in the code section, scroll down, and click on the Launch Binder button. This will open an interactive Jupyter notebook where you can follow along with the calculations. Please note that the initial launch of the notebook might take some time, but subsequent openings will be faster thanks to the cached files saved on your computer. Once the page is loaded, navigate to the folder on your left side, open it, and search for the file which has the IPYNB extension, and double-click on it. Inside the notebook, you will find a small introduction, a graphical representation of the tube components, 2 sections for the packages install and import, user input data, which allows you to modify variables related to the geometry of the column and socket faces, as well as some material data. Then you will find the cells with the formula for the initial stiffness, as is defined by Gomez, Neves, and Simões da Silva. Useful references for further reading on this topic are provided at the end of the notebook. The notebook then proceeds to the calculation of the initial stiffness for each column face separately, providing outputs for both the short face, indexed with 1, and the long face, indexed with 2, in the case of a tube with a rectangular cross-section. For a square cross-section, both variables will provide the same output. Following that, the equivalent frame models are presented. The notebook is divided in 2 main sections: the Harada equivalent frame models and the proposed equivalent frame models. Each of these sections further contains 2 subsections, namely IF, which stands for inertia full, and IEQ, which stands for inertia equivalent, as is explained in the description of the equivalent frame models at the very beginning. Lastly, the notebook concludes with references and notebook dependencies. Throughout the notebook, please keep in mind a few important points using Jupyter notebooks. Each cell can be edited by double-clicking on it. To run a cell, simply press the Run button, which has the play symbol in the top bar, or just simply use the shortcut Shift-Enter. Additional run options are available in the Run tab on the top bar. If the kernel stops, you can easily restart it. If needed, you can clear all the outputs from the Edit button. Now let's run all cells. Once you have the initial stiffness values for each tube component, which can be found Let's just scroll down. For example, in the Harada case for the inertia full here. Once you have these values, you will be able to define the beam to column joint element accurately and proceed with your structural analysis in OpenSys. If you are interested in delving into more details, I've included a link to my PhD thesis and some related papers in the video description below. I hope you find this video and the accompanying Jupyter notebook helpful. If you did, please consider giving it a thumbs up and sharing it with your friends. Also, don't forget to subscribe to my channel to stay updated with more content like this. Thank you for watching. See you in the next video. Bye.